Hello students, in this video lecture we will find out moment of inertia of holosphere and we will make use of these two tricks to calculate the moment of inertia. So firstly see, here we have holosphere which is hollow from inside. It means the mass is present only at the curved surface. So firstly we will assume that mass of this holosphere is capital M, its radius is r. So the curved surface of this holosphere will be 4 pi r square. So if you find the surface mass density sigma m, then it will be total mass of the holosphere divided by the curved surface area 4 pi r square. Okay. Now what we will do? We will divide to find the moment of inertia of complete holosphere. We will divide this sphere into elementary rings. So let me divide it into elementary rings. Okay. And we will find the mass of this elementary ring. Mass of this elementary ring will be equal to, that is dm. Okay. And the moment of inertia of this elementary ring, that is di, and it will be dm into r square. So if we know the radius and mass of this elementary ring, then we can find the moment of inertia of this elementary strip whose shape is ring. Okay. And if we integrate this, then we can find the moment of inertia of the holosphere. So here the trick is, we make use of the trick to find moment of inertia of holosphere. We will divide the holosphere, into elementary rings, and that moment of inertia, then we will find the moment of inertia of this elementary ring, that will be di, and then we will integrate it to obtain the total moment of inertia of the holosphere. So here we need to find the mass of this elementary ring, that will be equal to mass density into surface area of this elementary ring. So let O is the origin, O is the center of this holosphere, and we have taken r to be the radius, and this thickness of the angle made by the thickness width of this strip at the origin, at the center, that is d theta, and this angle is theta. Then this thickness will be equal to r into d theta. Now what we are to do? We are to find the circumference of this elementary ring, and for that you have to find out the radius of this ring, and from here you can see the radius will be r sin theta. So the circumference of this ring will be 2 pi r into sin theta. Okay. And the area of this elementary strip will be equal to circumference into the thickness width. So from here you can take idea of the mass of elementary ring, and it will be the surface mass density into the area of elementary strip, and that will be 2 pi r sin theta. This is the circumference into the thickness, and the thickness is r d theta. So in this way you can find the mass. Now we are to find the moment of inertia di of this elementary ring, and that will be dm into r square. And here r is the radius, that is r sine theta. So if you substitute all these values here, then you will get sigma m, this is as it is, then you have 2 pi r into sine theta into d theta, r into r square, and then you are left with this factor. Okay, this is the value of dm. Now you are to multiply dm by r square to find di. So r square here is r sine theta. So if you put the value of small r square, that will be capital R square into sine square theta. So this will give you the moment of inertia of this elementary ring. Now you are to integrate it. Okay, so if you are to cover the complete curved surface area of the holosphere, then you have to change this angle from this reference line to this. So the angle covered here will be from 0 to pi. Okay, and here theta is the only variable. So to find the moment of inertia of the holosphere, you will integrate it, and then you will get the moment of inertia of the holosphere, where mass is present only at the surface. So here you will get 2 pi r square into r square, that will be r raised to power 4, and you will get 2 pi r raised to power 4, and then you have sigma m, surface mass density, whose value is this. Okay, you can take these constants out of integration, and then you have limits of integration 0 to pi. Okay, and then you have sine theta into sine square theta, that is sine cube theta into d theta. So further I have told you, I have written here the formula of sine 3 theta. Okay, because you are to find the value of sine cube theta, and from this relation you will find the value of sine cube theta in terms of sine theta and sine 3 theta. So if you substitute the value here, then you will get see here, sine cube theta, this will be equal to 1 by 4 3 sine theta minus, take this factor on the right hand side, and you will get sine 3 theta. Okay, if you substitute its value here, then you will get moment of inertia I of holosphere, that will be equal to these factors, and if you put the value of sigma m, this will be m by 4 pi r square, and you will see here pi will cancel, and here you have r square, so r raised to power 4, it will cancel, and you are left with, I am writing it here, that is capital M, then you have r square, okay, and divided by 2. So this factor is left if you substitute the value of sigma m, and here you will get integration 0 to pi. Okay, you have 1 by 4, I am taking it outside, so it will become 8. Okay, then you have 3 sine theta minus sine 3 theta, bracket close, and then d theta. Now you are to integrate it, and finally you will get the result. Okay, integration of sine theta will be minus cos theta, and integration of sine 3 theta will be cos minus cos 3 theta by 3, and you are just to put the limits 0 to pi, and you can solve, and finally you will get the moment of inertia of holosphere, that is 2 by 3 mr square. Okay. Okay class, now we will find the moment of, so class here we have calculated the moment of inertia of hollow sphere about an axis which is passing through its center of mass. Okay, you see O is the center of mass of this hollow sphere, and this is the axis which is passing through its center of mass, that is O. If we have an axis which is passing through, which is along the tangent, okay, and let me take this axis AB. So we have calculated the moment of inertia of hollow sphere about an axis which is passing through center of mass, that is AB, and this axis is A dash B dash. So this axis is passing through the along a tangent, okay, and the moment of inertia of hollow sphere about a tangent will be equal to A dash B dash. You see here A dash B dash is the tangent. So here you will make use of parallel axis theorem, and which is moment of inertia about the tangent is moment of inertia about an axis passing through center of mass, and mass of the hollow sphere into the perpendicular distance between the axis passing through center of mass and the tangent. So that is r. This distance is r here, okay, and the mass of sphere, that is capital M. If you substitute the value of this, that is the moment of inertia about AB, and add it with mr square, then you will get, this value is 2 by 3 mr square plus mr square, then you will get 5 by 3 mr square. Okay, so this is another subtopic of this topic. One more thing you can do here is you can find the moment of inertia of a hollow sphere. Here we have taken the thickness very small. We have assumed that the mass of the hollow sphere is just distributed over the surface and the thickness is very small, and if we consider that this is of some definite thickness, you can assume it like this. This is a cell, okay, this is a cell. Then you will have two radius, one is the inner radius and another will be the outer radius, and you can find the moment of inertia of this cell from this relation. Okay, so let me do it again. In that case, the mass density, surface mass density, that will change. Now class, we will extend this topic for moment of inertia. We will find here moment of inertia of a cell, So here this is a special case in which the hollow sphere here in the previous topic, it was of negligible, I will write here, negligible thickness. So we have violated the concept of thickness in the previous case, and here we have cell. So the difference in cell and hollow sphere is that this is also a hollow sphere, but here the thickness is not negligible, so you have to count it. Okay, so let me make a cell here. So this is how a cell look like. You can see here it has a volume. Okay, so mass is distributed within this space. this is the space, okay, and we are to find the moment of inertia here. To find the moment of inertia, we will divide this cell into hollow spheres. You can see, you see here, this is a hollow sphere. This is the trick which we will make use, because we know the moment of inertia of this hollow sphere whose radius is r. This is the center. If we integrate the moment of inertia of this elementary hollow sphere within the limit r1 to r2, then you will get moment of inertia of the cell. ठीक है? So now class, we will make use of this formula. Here we have, firstly, what we will do, the trick is, we will divide the cell into hollow sphere, into elementary hollow spheres of mass dm. Okay, then find the moment of inertia of this elementary hollow sphere, and that will be di equal to dm into r square. You see, the moment of inertia of hollow sphere is 2/3 mr square. So here the radius is small r, and the mass of this hollow sphere, that is dm. Okay, so here the relation will be dm into r square, and r vary from r1 to r2. Okay, so you are to integrate it. Now our task is, let us suppose the mass of this cell is capital M. Okay, and you have seen here the mass is distributed over a volume. Okay, and you have to find the mass density, volume mass density. The volume mass density in this case will be equal to mass of the cell divided by the volume. The volume here is 4/3 into pi r cube, and here the volume will be r2 cube minus r1 cube, because this is hollow from inside. Okay, so from this total volume you will decrease the volume of the sphere of radius r1. Okay, so in this way you will get the volume, and here this is the volume mass density of this cell. If you want to find out this small mass of this elementary sphere, then you have to find the volume enclosed by this shaded white elementary hollow sphere, and this will be, the volume of this will be 4 pi r square. You see, this is the radius of this hollow sphere. So the inner curved surface area will be 4 pi r square, and if you multiply it by thickness of this elementary hollow sphere, then you will get the volume of this elementary hollow sphere. Okay, and let this thickness is dr. So here I have taken this thickness dr. So you are to multiply the curved surface area with dr thickness, then you will get the volume. So this will be the volume dV I am writing here. So this is the volume of this elementary holosphere, and if you multiply it by the volume mass density, then you will get the mass of elementary holosphere, that is dm. So it will be rho m into dV, and this will be equal to dm into dV. dV is there, that is 4 pi r square into dr. Okay, now you have to simplify it. You have to integrate this relation. You have to substitute the value of dm, and you have to integrate it within limit r1 to r2. Then you will get the moment of inertia. Okay, so class, here you see you are not finding the elementary. We don't have elementary ring here. This is elementary holosphere. Okay, so I have made a mistake here. This is elementary holosphere. So from here, if we find the moment of inertia of elementary holosphere, then it will be like this. Okay, and here you have r square. So I have left here 2 by 3. So please keep this in mind. So now you are to substitute the value, and then you will integrate di to get moment of inertia of cell. Okay, so from here you see you have 2 by 3. You can take it out of integration. Then you will put dm, the value of dm, and this complete factor will give you the mass. Okay, so you can take the mass density into 4 pi. Okay, these are constant. You can take them out of integration, and then you are left with r square and dr. And you have one more r square here, so I can write it r raised to power 4 into dr and its integration. Okay, from the inner radius to outer radius r1 to r2. So class, here you see, you know the integration of r raised to power 4 is r raised to power 5 by 5. Okay, and you are to substitute the value of rho m, mass density, which is given here. Okay, and to simplify it, then you will get moment of inertia of cell, that is equal to 2 by 3 into mass density, that is total mass of the cell, divided by the volume in which mass is dispersed, that is 4 by 3 pi. Then you have r2 cube minus r1 cube. Okay, so this is the value of mass density. Then you have 4 pi, again 4 pi, and from here you will get r2 raised to power 5 by 5. Okay, minus r1 raised to power 5 by 5. So from here you can see, you can write it like this, a minus sign here, and you can take 5 out. Okay, so if you simplify it, then you will get 3 will cancel, 4 pi will cancel here, and you are left with 2 by 5 into mass. So I am writing the relation here. Final relation will be 2 by 5 mass of the cell, and then you will get a factor, that is r2 raised to power 5 minus r1 raised to power 5, and divided by this factor, that is r2 cube minus r1 cube. So this is the moment of inertia of a cell. Thanks for watching the lecture.